Welcome, everybody. I hope you have great lunch. As I mentioned, this is the last talk of the term. We're very excited to have Dr. Bichoy Bahr with us, giving a talk of the doctoral dissertation, which means he did superb work in his area of expertise, and we put together a panel and unanimously decided that he was the guy that should give the talk this time. A little bit of the introduction for Bichoy. I happen to have the pleasure to have taught him in 777 MEMS. But before that, he's from Egypt, and he studied in Egypt his undergrad and master, and then came to the group of Dana Weinstein and did all these amazing things about resonators. I'm not myself a resonator expert, but I truly believe that the work that he did is groundbreaking. And it has the feature that can be easily integrated with CMOS, as you're going to discuss. So he's going to join the TI,
yep.
In June. And without further delay, we'd like to hear about your very exciting research, and welcome to the seminar.
Thank you. All right. Thank you, Luis, for the very nice introduction. So today I will talk about monolithically integrated MEMS resonators in a standard IC technology. And as the outline of my talk, I will first start by the motivation. I will talk you a little bit about MEMS resonators, and then we'll start talking about what do we mean by unreleased MEMS resonators. These are completely solid devices embedded inside the CMOS die, and we will see it's very exciting. And to do that, we'll have to talk about phononic crystals, phononic waveguides. We will also see a lot about numerical optimization. We will see some theory. And then after that, I will switch gear to the GaN mimics technology, and we will look at resonators and oscillators in GaN mimics as well. So let's get started right away. Why I did all my work, it's basically for the frequency sources and filters. Whenever we look around us, we find that we are surrounded by diverse electronic devices and equipment. And all of them, they need frequency sources and filters, either to act as a local clock for digital circuits or to act as a local oscillator for RF communication capabilities. So if we manage to improve the performance of oscillators and filters, and if we manage to get them integrated inside the CMOS die, we will probably affect unlimited number of devices. We can just imagine the possibilities that we can do. It's a breakthrough similar to what we did with integrated circuits back in the 1960s and 1970s, when we figured out when we can pack all these circuits together in a very tiny chip, we could achieve so much more. So the potential here is very similar. Not only that, we notice now in the past few years, there have been lots of new applications like wearable electronic devices, smart chronic medical implants, autonomous wireless sensors, and all of these applications, they share the same requirement for low power, ultra compact form factor, and some of them require high frequency to communicate large amounts of data. So in the past decades, we have been relying on our quartz crystal to act as our resonator, our mechanical filter, and we used it for local oscillators. But as we can see, its form factor is getting very bulky. It requires an extra pin on each chip. It takes space on your PCB. So it doesn't really fit very well in these new applications that we are talking about. And so my goal in this whole work was to actually get the MEMS resonators inside CMOS. And why in particular MEMS? Why not use just LC tank circuits on chip or quartz? Well, MEMS resonators, I believe they are the way to move forward, as many researchers do, and this is due to their great benefits. They have very high quality factors. They have very small footprint, much smaller than an on-chip inductor, for example. And also, they can be integrated with CMOS, which I like to call the MEMS dream. Everybody doing MEMS out there, just his hope is to get his MEMS device integrated with CMOS. So that's the dream of the MEMS technology, and some other cool capabilities like tuning and resonator arrays. But they also come with their challenges. When we talk about MEMS resonators that mechanically vibrates, they need to have free surfaces in order to vibrate and move. And once we start talking about free surfaces, then we start getting into trouble. Why? Because our device will be sensitive, will be highly sensitive to the environment. It will be affected probably by the pressure It will be affected by the humidity adsorption. It can be affected by particle deposition. So all of that leads to packaging challenges. We need to hermetically seal our MEMS resonator in order to protect it from all these environmental conditions. And let alone this basically free surfaces also create some problems during processing. They might result in lower yield due to stiction and other problems. So what if we can just get rid of all of that, get rid of all these released operations and have a completely solid MEMS resonator? It doesn't make much sense to talk about something that vibrates while it's completely solid, but that's what we will see today. And the final thing I want to say also, CMOS integration is still a challenge for MEMS. It's not settled down yet. And the commercial solution, as we can see here, basically people rely on two-chip solutions. They fabricate circuits on their own, MEMS on their own, and then they wire bond them. And once you look at this picture and you say, oh, I want to operate at 10 gigahertz or something, you start getting scared by all of these wire bonds, and it's not really nice. So the approach I'm trying to take is basically have the MEMS resonator encapsulated inside the CMOS die, just like we see here. And not only that, I want it to be fabricated just like any other transistor or circuit. I don't want to do any post-processing whatsoever or any special vacuum packaging or anything like that. Just send out my layout like we do with any circuit design and get back the chips. They will have the circuits and have a MEMS resonator inside them. So this is very advantageous, actually. This gives us the opportunity to access the front end of line materials, which are very high quality materials. They have very low losses. And of course, it will be completely solid as we please. The previous efforts in MEMS integrations, there have been so many efforts like the CMOS first processes, the CMOS last, MEMS first, MEMS last, and CMOS MEMS, which works in the BOL. But most of these, they always require the protection of one device while the other is fabricated. So when you do the MEMS first, you need to encapsulate it, go fabricate the circuits, and then get back to the MEMS, release it, or it doesn't work. It's not very convenient. So the challenges to doing something like that is, of course, how, first of all, the biggest problem, how you can get a solid entity like the CMOS die to vibrate internally. That's the first problem. The second problem is transduction, how we can excite waves. If we imagine that we can confine the waves, the acoustic waves inside, how to excite them and how to detect them. So the easier problem first about exciting the waves and detecting them. For exciting the waves, we will use electrostatic transduction, but not the traditional one with air gaps, because we don't want any air gaps. So instead, we will use electrostatic transduction with a dielectric. And this is basically works like a parallel plate capacitor. You have dielectric in the middle. And when you apply voltage across the capacitor, you got positive and negative charge, and they start attracting each other. If you modulate the voltage, the plate will start vibrating. And of course, we have lots of capacitors in CMOS, and mostly we have MOSCAP, which is just a MOSFET. This is available abundantly. And on the other hand, for sensing, we would use active piezoresistive sensing in the form of just a MOSFET with some current running through it. And the stress in the resonator in our device will basically modulate the mobility of the channel, and we can sense this as variation in the bias current.
You say no air gap, but you're showing an air gap in the picture on the left.
Yes,
Why do you say no?
This is the next slide. Yeah. So no air gap inside the device. So this is a bar resonator. It's a contiguous bar. It still has free surfaces, and this is what I will solve today. I will get rid of these free surfaces. So this was the very first demonstration of basically electrostatic transduction with with MOSFET sensing by my advisor, Dana Weinstein, back in 2010. So she called it the resonant body transistor because we have a transistor inside and we have mechanical resonance. And you can see here it was just a bar resonator, and it had one dielectric for transduction and another dielectric that works as a MOSFET. So this was a step in the right direction, meaning the bar itself is contiguous. But of course, the challenge, how do we get this contiguous bar inside the CMOS die, inside completely solid CMOS die. So the first people to address this problem were my friends in our research group, Wentao Wang and Radhika Marasi. And what they did, they used the concept of Bragg reflectors. I guess most of us are familiar with Bragg reflectors from optics, when you basically have transparent dielectric layers, and when you stack them up with the correct thickness, that's exactly lambda by 4, you start getting strong reflections. So they start acting like a mirror. And it turns out we can do the same thing in acoustics, and people have demonstrated the same idea of acoustic Bragg reflectors back in the 1960s and also in the early 90s to do solidly mounted resonators. So what they did here, they were the first people to do it inside CMOS die, in particular in the IBM 32 nanometer SOI technology. And so this is how the device looked like. This is our bar, the resonant body. It's basically made out of the polysilicon and polysilicon gate and active area and silicon active area underneath. And then we have this island of silicon separated by oxide, and this makes our Bragg reflector. So this device suffered from or faced several challenges. First of all, we noticed a very low quality factor. They got quality factor of 30 at 11 gigahertz, which is not that great for a mechanical resonator.
What does DRC mean? DRC restrictions?
Yeah, DRC is the design rule check. This is usually available in CMOS processes. They always tell us if you want this pattern to come out right in the fabrication, you cannot make it smaller than this dimension, or you cannot draw lines closer to each other. So in the front end of line layers here, the DRC restrictions were very severe. Like there is very little that you can do to control the dimensions or separation. So that's the first problem in this device. The second problem, if we look closely at the Bragg reflectors, they are actually very thin. This thickness is probably 100 nanometer or something like that. So as a result, what happened, we found that the vibration in this resonator, they start radiating out all the way on top and the bottom. So from now on, you will notice my language will start to drift away from the MEMS community. I will start to talk about radiation. I will start to talk about dispersion, about scattering. I will basically start to use wave notation. And why is that? Because I'm working in completely solid material. It's not anymore a suspended bar. It's just a continuous medium as you have with like the free space, for example, for electromagnetics. So at this time, I joined Dana's group, and it was my task how to solve this problem, how to get vertical confinement, confine the waves in this thin slab. And I kept working very hard on this problem, scratching my head, lost lots of hair due to it. And even I tried Chuck Norris approach, like just stare for it long enough, nothing worked. And then I decided, okay, let's try something different. Let's first take away all this mechanical polishing fill, all this CMP fill. And this is usually included in the CMOS process so that the CMP works correctly. And the reason we don't like it, it's placed randomly, and it's probably responsible for all these spurious modes that we see. So took the CMP fill out, but I had to put something in there, right? Because I didn't solve the problem. I still have this continuous medium all around me. And so my staring hours at the problem didn't go to waste. I started to actually realize that this BOL metal stack, it looks very regular. And it kind of looked periodic somehow. And also, the material used in this particular technology was copper for metallization and silicon carbohydroxide as a low-K dielectric, which I like to call it SiCO, and that fits the theme of what we are doing here. So they have very large acoustic impedance mismatch. And acoustic impedance is just very similar to the characteristic impedance in electromagnetics. So what does it mean? It means whenever I have an interface between copper and SiCO, I will get lots of reflections. So they can make good reflector, but how to do it? Well, owing to the shape of these metal lines and how they look periodic, so I said, okay, this should be ideal to make phononic crystals. So what are phononic crystals? These are basically 2D or 3D periodic structures, and they have band gaps in their dispersion relations that can prevent wave propagation in a certain frequency band. So my first trial, and it turns out to be very good actually, was just this 2D phononic crystal, just a bunch of parallel metal lines. And from a CMOS point of view, from a process point of view, these are very good structures, because in CMOS we have all this bus routing, so it doesn't annoy the process at all. I'm not asking for something strange. And so when I started to analyze this phononic crystal, basically we take a unit cell, impose periodic boundary condition, and then basically look at the solutions in the K-space, just like what we do in solid-state physics. And we do eigenfrequency analysis to get all the possible modes for all possible K vectors. And when we do that, I basically got a staggering 85% band gap. You see all this huge gap in frequency. It's about 3.8 gigahertz wide, where no waves can propagate in any direction inside my phononic crystal. So I said, well, okay, that looks great. And this is the first device I made myself in IBM 32 nanometer SOI. You can immediately recognize here the phononic crystal on top. And I have my resonant cavity here. And in this resonant cavity, I use 2 MOS caps for driving and 1 MOSFET for sensing. And the other important thing is that I basically made the structure to be uniform in the Z direction. So out of plane, we have everything uniform as we go along. And we will see that this basically reduces scattering. So I measured this device. It was great. I got quality factor of 252. That's 8 times better than what we had earlier at 2.8 gigahertz. But still, it's not enough. We want to go much higher than that. So in order to improve the device, we first need to understand exactly what's happening. Why do we get this quality factor? This is just a comparison that demonstrates why it's important to have uniformity in Z direction. We tried basically the same exact device, except for the contacts, for the metal contacts, instead of using the regular square contacts available in CMOS, we tried rectangular contacts. And IBM didn't like it. They weren't happy, but we made it. We took the risk. We told them we are grown up enough. We understand what we are doing. Just let's do it. And it turns out, indeed, when you have uniformity in Z direction, you can get higher quality factor and you can get lower spurious mode because you have lower scattering. And we'll comment about that much more later. So this is the FEM simulation results, and we notice we got the resonance frequency correctly, 2.8 gigahertz, and that's not magic work at all. In the beginning, when I did the first simulations, I couldn't match the resonance frequency, but what I did, I went back, measured the exact dimensions from the SEM, and basically tried to back calculate the material properties, because there were so many materials that are unknown, or IBM didn't want to disclose them to us. So here we look at the resonance mode of this resonator, and it looks very good to me. At least the phononic crystal is working. We get lots of reflection from the phononic crystal, but still the waves are propagating in these directions. They are propagating outwards. And I said, okay, we need to find a way to confine the waves in the horizontal direction, but something else kept me up at night all days. And I keep asking myself and say, okay, self, we put a reflector on the top, and waves didn't go to the top. That's nice. But why don't they propagate in the bottom? That was a very interesting observation to me. It looks like the waves are propagating horizontally, but they can't go down, and I don't have anything down. So at this time, I basically started approaching the photonics community much more, and I attended Professor Stephen Johnson classes, almost all of them. And I just learned, I actually constructed a waveguide. As you can see in this picture, the waves just propagate at the surface. And to understand why this structure can guide the wave, we have to look at the dispersion characteristics of this structure. So first, it's periodic in X. I took here a vertical section where I have the phononic crystal on top, just one period from the phononic crystal. And I have here the bulk wafer in the bottom. And I apply periodic boundary condition in X direction. and I use the x component of the wave vector to parameterize my solution because it's conserved by virtue of the translational symmetry. And I start looking at all the possible eigenmodes. So first, I find the phononic crystal bands that can propagate upward in the phononic crystal. That's expected. Next, I find this, what I'm calling here, a sound cone. And this is similar to the photonics people light cone. The sound cone is basically all the plane waves that can propagate into the bulk wafer. And these plane waves, they have a dispersion relation omega equal c times magnitude k. So if you want to look at only kx, only the x component of the wave vector, it will be omega bigger than ckx, because ky can have arbitrary values. And after that, we got this 3 blue modes here. We got this white region with 3 blue modes. And this was very interesting because this white region, it's basically the band gap of the phononic crystal, so waves cannot propagate upward, and it's also below the sound cone. So what does it mean to be below the sound cone? It basically means the kx component of the wave vector needs to be bigger than the wave vector itself. So the only solution for this to happen is for ky to be imaginary, and we get evanescent waves in the y direction. So waves doesn't propagate down, instead they decay evanescently with exponential decay. So this is why any mode here, it's basically confined between the phononic crystal and the bulk wafer. It cannot propagate in either of them. And due to the confinement and localization of energy, we get these discrete modes. We get these blue modes that have discrete spectrum instead of a continuum. So that's great. That explains why waves doesn't go down. But then the next step, how do we prevent them from propagating laterally? And so I said, OK, now I have a waveguide. What can I do with it? And as I know, if I change the dimensions slightly, all this dispersion relation will start shifting accordingly by basically the wave equation transforms linearly under coordinate transformation. So what I did is that I said, OK, here is my one design of a waveguide that I have. And now you can see I included the polysilicon gate and all the contacts and everything. What if I took the same structure but made a bigger period? Say, increase the period by 10%. And as I expected, all the frequencies will just scale down. And so when I look at this region here, these 2 waveguides, I find that the modes in this waveguide with the original dimensions are basically looking into a band gap in this waveguide with a bigger dimension, which means they cannot propagate, they cannot penetrate this waveguide. Instead, they will all get reflected. So when I see that, I understand, OK, I can make a termination. Except the only thing I have to guarantee, I have to operate around this kx equal pi over a. And what does it mean to have kx equal pi over a, where a is the period of my waveguide? It means when I move from one period to the other, I should see a phase shift of 180 degrees. And there is a very nice physical picture to explain why this particular phase shift results in wave guiding. Because if you go far enough down in the bulk and look at the transducers, you will see radiating waves that are 180 degrees out of phase. So as you stand away, these waves will start to destructively interfere, and you will not see any radiation. So that's the physical intuition. That all looks good. And this is basically the structure I envisioned. And I said, OK, I will have a main waveguide section here with the transducers, and then I will have a termination waveguide section here and another termination there, and basically form a resonator. So the final structure I converge to, this is how it looks like. We are looking at the left half. It's symmetric around this axis. And this is my main waveguide section. This is my termination waveguide section. It has a bigger period, as you can see here. And I also started using fully differential driving. So instead of single MOS cap to drive, I started using fully differential to apply positive, negative, apply basically the 180 degrees out of phase force. And why is that? We need this for kx equal pi over a. And then we have here our sensing MOSFET and an isolation gate to reduce the feed through. And this device footprint is basically 4 micron by 13 micron. That was all good, but of course, life is not that easy. Once I did that and I started simulating it, I expect to get perfect resonator. But what happened is that I found at these locations, in particular here, when I start the termination waveguide, and at this location when I have the isolation gate, I start getting radiation all the way to the bottom again. And why is that? This basically happens because of scattering, because now we have a waveguide and we suddenly put an abrupt termination to something else. So this generates scattering. And so what we need to do first, we need to match the characteristics of the different waveguide so we avoid this scattering. And to do that, I resorted to numerical optimization. I worked a lot with Luca Daniel on this problem. It's a very hard problem. And what we can do is we say, OK, we will have all our waveguide dimensions as parameters, and then we try to maximize either the quality factor, Q, or the electromechanical transconductance, the transfer function of the device to get the highest output signal. But of course, the problems when we do that, first, in numerical optimizer, what it will do, it will start changing the parameters and look at the objective function, like look at Q or the transfer function. But as it changes the parameters, the resonance frequency will start to shift. So my first problem, I need to consider a large simulation bandwidth to be able to capture the resonance peak. The second problem, I'm looking for high Q resonators. I'm looking for high Q peaks, so they will become very narrow, which means I need to take lots of simulation points in the frequency domain to be able to resolve it. So I have wide bandwidth, lots of points, and that's basically a recipe for a very slow FEM simulation. So a single simulation ended up taking 1 hour just to evaluate a single design. And if we put that into an optimizer that will evaluate the objective function hundreds and hundreds of times, we can never finish. So working with Luca Daniel, we came up with several techniques to basically address this problem. The first technique is basically using model order reduction through Padé approximation. And this is about finding an approximation for the transfer function. Instead of solving at each frequency point, we can just approximate the solution like when you do with Taylor series around certain points, and that would be enough. The second thing is memoization. And this means whenever I run a simulation, I save all the previous results. So when the optimizer asks for a new design, I go back to these results, and I can estimate where my resonance frequency will be. So I don't need to simulate the entire large frequency band every time. I just focus on where do I expect to see the resonance frequency. And of course, we can evaluate the gradients in the same idea by finite difference, just run very narrow simulation. And this is how the whole flow looks like. So we have an optimizer working in MATLAB using the fmin_con function, and it generates design parameters, ask to evaluate the objective function. We do memoization search, select simulation bandwidth, run COMSOL for finite element modeling, and with Padé approximation included, and then calculate the objective function, save the state. And the same thing happens for the gradients. When we did this, we found that we can actually improve the optimization speed by 40 times, which is huge improvement. We can basically optimize the entire RBT structure into FEM simulation in less than a day. And it's important to note that when we did this work, it doesn't just work for MEMS resonators. You can apply it to any device that needs frequency simulation. So this is great. This is a big addition to the MEMS community that they can use, and hopefully we will see much more devices optimized with this framework. So this is optimized devices now with the termination and everything in place. And you can see we got much better confinement. The waves are not leaking in any direction. And we fabricated in IBM 32 nanometer SOI. You can see now the phononic crystal, the driving gates here, the sensing transistor, and the termination. And this is a close-in view for the sensing FETs as well as the isolation. And when we measured these devices, I got a quality factor of 13,500, which is very impressive. This is 33 times better than the previous generation. And of course, the product F naught Q is 4.3 times 10 to the 13. That's almost record high. And the area is just 2 times bigger than the previous generation. So now I didn't stop there. I said, OK, we keep talking about scattering, scattering, scattering. So what is the scattering? We know that acoustic waves are similar to electromagnetic waves. But to what extent are they similar? Are they qualitatively similar, that they are all waves? Or can we mathematically prove that if something works for photonics, it can necessarily work for acoustics? And so I was very inspired by Professor Stephen Johnson's work on this topic when he basically formulated his photonics problem in a manner very similar to quantum mechanics. And so I followed in his steps, and basically starting from the elastic wave equations that we have, I said, okay, let's try to do something similar. Let's define them in a way that looks like quantum mechanics or photonics and see what we can get. So I started by basically defining an abstract state ket using Dirac notation, and I selected the state ket specifically to have the velocity and the stress. This selection is very important, and basically define this inner product. And then the next step, what I did is separate the derivative, basically expand the gradients from this wave equation into transverse component and z directional derivative. And why in particular z, or what I'm doing here, I noticed that in all my work, I'm interested about these waveguides. And when I talk about scattering, I talk about having a waveguide and then some termination happens and I get scattering. So I want to understand what happens to the wave as it propagates along this waveguide. So for this reason, I did that. I said, okay, let's separate the z component, the propagation component on its own and see what we can get. And of course, after substituting back, I got to this very nice wave equation here in terms of the abstract state ket that has an operator A and this operator Z. And this is how the operator A looks like after some heavy lifting in vector calculus. I can prove its Hermitian. So we ended up with very nice generalized Hermitian eigenproblem. And if you look at it long enough, it looks actually very familiar. Maybe it will look even more familiar if instead of A, we call it H, and just drop the Z for now, let's forget about it, and add IH bar. This is basically the time-dependent Schrodinger equation. It has exactly the same form as the equations that govern acoustic wave propagation in solids. Even better than that, if we look at the inner product of psi A psi, this is basically corresponds to the stored energy density along the waveguide. And the product psi Z psi corresponds to the power propagating through the waveguide. So when doing that, this formulation here with the inner product defined before exactly matches Professor Stephen Johnson formulation for the photonics. This is the exact equations. They are not an approximation. There is no something that looks like it. No, this is the exact same equation with Hermitian operators. And so this is fantastic because we can just borrow lots of concepts and lots of structures that we know they work in photonics, like waveguides, couplers, all of that. We can just borrow them and implement them in acoustics. So I will show you just one application here. But of course, this analogy can extend it way beyond that. And my application will be for the coupled mode theory, how the different modes propagating along a waveguide starts to couple whenever we have perturbation. So to do that, we solve it like in quantum mechanics. We just assume the solution at any z will be a superposition of the local solution, of the instantaneous solution, if you talk about time-dependent perturbation in Schrodinger equation. But of course, here it's z. So this is how we will express our solution. And then we substitute in the equations that we have, our master equation, and we get this rate of change for the coefficients, for the expansion coefficients. So it tells us that as we go along, the expansion coefficients for the different modes will change, which means I can start by a mode that I will call mode 0. And after propagating through the waveguide, I may end up with mode 0, 1, 2, and 3. So here we also find that the rate of change of this coefficient basically depends on the perturbation in A. How much do you perturb the master operator? How much do you change the material properties and dimension? And not only how much, it depends on how fast, because it's derivative of this operator with respect to z. And it also inversely depends on beta, where beta is the component of wave vector along the propagation direction. And this looks very similar to basically Fermi golden rule, if you look at it from another way. And so the difference in beta tells me in order to minimize scattering, I need to make sure my modes are as far as possible in the K space, and I also need to have very slow transitions in the space. I don't need to make fast changes. And so this leads us naturally to the adiabatic mode theorem. If you want to reduce the scattering, just avoid any abrupt transition and make everything very slowly. As you can see here in this resonator structure, I have the termination waveguide evolves very slowly from the main waveguide. And so I implemented these devices again, and you can see here the stress distribution is now much, much better. It's well aligned with the gates because we don't have this abrupt transition and we have lower scattering. And this is the measurement results for the device. It got quality factor of 9,000, but that's not because of the terminations. This is just different dimensions from what we have earlier. So they are potentially different designs. If I wasn't using the adiabatic transition here, this device will have a quality factor of 6,000. So the adiabatic transition helps increasing quality factor by 30%. And moving on, I also try to implement the same concept in FinFETs. Why FinFETs? Well, we love them electrically for so many reasons, but also it turns out that this periodic fin structure, it can confine the wave in the same way as we have seen with the periodic structures that we have. And this is a device in Global Foundries 14 nanometer FinFET technology, and I taped it out with them during an internship. And we are still waiting for the results. It takes forever to fabricate this thing. So just a quick glance, in order for these devices to be useful for circuit designers, they need to have models that can fit in their CAD tools. And so for this purpose, I worked on basically compact modeling in Verilog A. And just to give you a quick high-level idea, this is how a model for such thing is constructed. You have different modules, a module that basically simulates the resonance, a module that simulates the driving, and a module that simulates the sensing MOSFET. And of course, you have to guess the modules that simulate the sensing MOSFET, it have to be a complete MOSFET model. So yes, that's true. I used here BSIM model and basically modified it to support the variation in the channel dimensions and stress. And you can find, I released 3 versions of this model. You can find them on nanohub.org. Okay, so what's left to improve in the device? Well, the only thing left is the amplitude of the transfer function. And to improve that, basically lowering the insertion loss, we need to change the transduction mechanism. The electrostatic transduction doesn't work as well. So how we do that? Well, we were looking for piezoelectric materials, and these are started to appear in CMOS technologies. They are used to basically make F-frames into the form of ferroelectric materials. So we were looking at Global Foundries technology here. They have a ferroelectric layer inserted in their gate stack, so we were considering that. And we are also working with TI on this, on their technology, that they have specific FE-cap devices used independently. So we are trying to use either of these technology now to basically enhance the amplitude of the transfer function, which will enable us to get low power oscillators. But we start thinking, okay, if we need piezoelectric transduction, and we are stuck with CMOS, well, it's fine. But what happens if we move away from CMOS? There is actually a very nice piezoelectric material that happens to be also very nice from an electrical point of view, and it's widely used today for RF circuits and power applications. And it also has its integrated technology. It's called MEMS. So I guess you think you can now see what material I'm talking about. I'm basically talking about gallium nitride. So we said, okay, fine. If it's a little bit hard now for piezoelectrics in CMOS, why not to use gallium nitride? And gallium nitride, of course, it's a very good electrical material. We know it has this, the AlGaN-GaN heterostructure has this potential well, and this 2D electron gas, which has very high sheet charge density and mobility, and this is why it's used for the high electromobility transistor. But it also turns out to be a very good electromechanical material. It's piezoelectric because of its Wurtzite crystal structure, and it has a very efficient coupling coefficient. Here it can go up to 2%. Also, it has high acoustic velocity, which means we can scale up to higher frequencies easily, and its intrinsic losses are pretty much low, so we can still get high quality factors as well. So we said, okay, let's use that. And it also happened, I had, in our group, we had Laura Popa. I'm pretty sure most of you know her. She was working on developing these LEM mode MEMS resonators inside GaN mimics technology. And what she basically achieved, she can finally make these resonators side by side with HEMT transistors. So we get, in the same idea as we had in CMOS, we can now get a MEMS resonator side by side with circuits. And so this is how the resonator looks like. It's just a regular release resonator. It's not completely solid anymore, but that's fine. This is what we can do. And she achieved basically a quality factor of 5,000, which is very impressive for these GaN devices. So when I look at a simplistic RF transceiver and I say, okay, what can I do with these MEMS resonators and transistors? Well, there are so many places where we can use filters, and of course, we need a local oscillator. So I decided, okay, let's attack this problem. Let's start with the hardest thing first. Let's try to make a local oscillator that's monolithic. We have the MEMS and circuits. Let's do it. And so indeed, I did Pierce and Colpitts oscillator, designed them into Laura's technology. And so why Pierce or Colpitts? They are very simple. They only require one HEMT, very small and low power consumption, of course. But I ran into a very unusual problem, or at least it was unusual for me. I come from a circuit design background in CMOS, where we have this huge foundries that gives you all the models and a well-featured design kit. But this wasn't the case. I found I have HEMTs. I have them physically fabricated, but I have no models for them. I don't know how they behave. I don't know how to simulate circuit with them. And so for this, I basically had to go to the MIT virtual source model developed by Usual in Professor Antoniadi's group. And I had to play a little bit with the model, adding some features like output kinks and some non-idealities in my simulation. And I also did some extensive work in order to extract the parameters of the MVS model to fit my actual devices. And so this solved the problem of the HEMT, and still for the passives, like resistors and capacitors that I need, I used for resistors a 2DEG layer itself. It has a very good sheet resistance, and we had an MIM cap in the process. So this is how it looks like at the end. This is an entire oscillator, completely monolithic. You can see here the MEMS resonator, and you can see here the HEMT, the resistor, and MIM caps. And this is actually a pure MTL product that I'm very proud of, and you should all be proud of. It's completely made at MTL. The process designed at MTL, resonators designed and optimized at MTL, the transistor models also made at MTL, and of course, circuit design made at MTL. So this just gives us an idea how amazing this place is, how collaborative, how diverse, how many expertise we have here. So how well these devices performance? Well, they work very well. These are the phase noise measurement at 1 gigahertz, and power consumption. I have different versions with different power consumptions. Power consumption is on the order of 1 milliwatt and 5 milliwatt for the other one. And we get a noise floor of minus 130 dBc per hertz and minus 140 dBc per hertz for the higher power consumption. And compared to the state-of-the-art gigahertz MEMS resonators, we find that our devices made here at MTL are actually very competitive. First, this is a first-of-its-kind solutions that can offer both a monolithically integrated solution and can support multiple frequency on chip, because these LEM mode resonators, they have their frequency defined by lithography, not by the thickness of the different layers as in FBAR technologies. And for the power consumption, we got very impressive numbers, 1 milliwatt, which is much lower than anything else out there. Our figure of merit that basically relates the power consumption to the phase noise, I would say we are doing quite well, 206, when we compare to these two guys. But we are still behind these two works here. But for me, I'm very happy with that. Why? Because these were first, two separate dice solution. We have a single dice solution. We have much smaller area. And they also did it in CMOS technology, which means they had the process well figured out. They had the models. They had everything optimized for them. And these are not regular CMOS processes. These are 0.18. The process has been around for probably 15 years. So it's very different. It's unfair competition, if I may say that. But yeah, we are very proud of our achievement here. And also I did filters, basically lattice and ladder filters using the same LAM mode resonators because we can change their frequency lithographically. So it's very, very easy to tune them. And we have filters around 1 gigahertz and 2 gigahertz as well. And basically, at this point, I would like to reflect on what I have done so far. So first, we have seen an optimization framework implemented for MEMS devices in general. And we hope this will help lots of people out there in the community. Second, we have seen the operator theoretic formulation for acoustics that basically tells us elastic waves are identical to electromagnetic waves in terms of abstract mathematics. So if we have a concept in photonics that work because we have Hermitian eigenvalue problems there, we can directly apply it to elastic waves, and it's identical. It's not an approximation. We have also seen the major achievement of this work, the unreleased CMOS MEMS resonator, how to integrate these vibrating resonators inside completely solid die without modifying the process, without requiring any release or post-processing or packaging. And finally, we have also looked at the GaN mimic technology and how we can offer solutions for them in terms of oscillators and filters. And of course, from here, the applications are just limitless. For example, once we start integrating these resonators in CMOS and we can get oscillators running, they will be very tiny and very low power. So we can integrate hundreds of them in a single chip. And this immediately leads us to coupled clusters of oscillators and coupled array, which we can use for unconventional signal processing. We can use them for beamforming in radars. There are so many applications that are waiting for us to explore. And with this, I would like to conclude and thank all the people that helped me, especially Professor Dana Weinstein and Professor Luca Daniel. I was very honored and privileged to work with them. And of course, all our funding agencies, my group mates, and of course, the amazing MTL staff that helped me throughout my entire PhD, and they helped me a lot to achieve that. So thank you all, and I'm very honored to be here.
Thank you, Bichoy, for a very interesting talk. Now the room is open to maybe a few questions before our director hands over the award for best thesis.
I have a question. What is the physical displacement of some of the elements in your arrays?
It's very small. It's probably tens of picometers. It's very, very small. We have stress levels on the order of 20 megapascals. And so strains are in microstrain level kind of thing. And for these dimensions, like they're all in nanometers. So with microstrain, you just get very, very small displacement. And this is actually one feature of bulk wave resonator because they're completely solid, so they don't move as much. And this is the reason they are not affected by the environment. Like they don't care if something happens at the surface, or they just don't care. The movement is all internal and it's very small.
Bichoy, I actually have a question about the technology transfer.
Yeah.
Because you mentioned at some point when you were doing your photonic crystals that unless you got exactly right the dimensions, then the frequency you couldn't predict. I mean, so some of the actual performance aspects. Yep. And as you know, microfabrication has this
variations.
Spread. And
yes.
Maybe you have had conversations with your future employers, TI, about those issues. Can you tell us a little bit of how it would affect?
Sure. So in terms of process variation, I would actually like to show you studies that I did before, which is very interesting as well. So also from the theoretical analysis that we did, we figured out, okay, perturbation theories that we know very well from quantum mechanics applies here. And so the resonators are going to be affected only by the change in dimension where we have the highest energy storage in our elements. So for example, when we look at the metallization layers, where this is the thing that has the largest variation and the fab doesn't care too much about it, like it can have thickness variation, it can have misalignment, it can have all sorts of problems. So when I looked at how this perturbation in phononic crystal affects the device, in fact, the effect is minimal. Why? Because most of the device energy is stored in the front end of line layer. And here I did lots of simulations, for example, to see how the phononic crystal is affected, and the effects happens at the edges of the band gap. So since our device operates well inside the band gap, operates in this region here, it's almost unaffected at all by the variation in the BOL PNC. But of course, when we go down to the FEOL layers, if we start changing the thickness, the frequency might change. But by how much, this depends on the actual mode shape and how the energy is distributed. So it's not as bad.
Any other questions? Okay. Well, let's thank Bichoy again.
Thank you.
And I'm going to hand over the microphone to our director, Jesus.
Bichoy, it gives me really a great pleasure to give you this award.
Thank you, my honor.
This is a very impressive thesis, and I'm very pleased in particular of how well you have used the resources of the lab.
Thank you.
Both the CAD resources, the process design kits, the contracts that we have with the companies that provide us with fabrication services, but also the fabrication capabilities of the lab is really very impressive. This is a fantastic thesis, and I'm extremely proud of giving you this award.
Thank you.
Careful, it's heavy.